All right, so let's pick up where we left off last time, which was trying to reason through this mechanism here, where under acidic conditions, our aldehydes and ketones will react with water to form what we call a Chem diol. Okay? Under basic conditions, we saw that first step was nucleophilic attack. And we sort of started with this last time and said, well, that's not going to work out at all because my intermediate here would look something like this, where one of those oxygens were positively charged, but the other one was negatively charged, and that can't be allowed under acidic conditions, where I'm not allowed to have any strong bases. So nucleophilic attack will not be the first step under acidic conditions. Instead, we're going to have to use these protonation steps to manage our charges. All right? So by that I mean if we first protonate that aldehyde oxygen, something similar to what we saw in our mechanisms for alcohols under acidic conditions, where that first step was protonation of that oxygen. All right, now we have this oxygen with this positive charge, which means importantly that when my nucleophile comes along and attacks my water molecule, kicks that pair of electrons up onto that oxygen. That oxygen doesn't have a negative charge, but since it was formerly positively charged, it's now neutral. Or I guess I can just rewrite this as an alcohol group. All right, so importantly, my oxygen accepting that pair of electrons, now it does not become negatively charged, which again wouldn't be allowed under basic conditions. It's neutral, that is allowed. But my other oxygen, which was neutral as a water molecule, when it donates that pair of electrons forming that new bond, now it's got 3 bonds, and so it's positively charged. Are we allowed to have these under acidic conditions? Yeah, this is fine. We're just not allowed to have any strong bases. This thing here would be considered a strong acid. Well, acids are allowed under acidic conditions. We're not quite there, though. We got one more step to go in order to create our Chem diol. We simply have to deprotonate that oxygen, so we're going to need a base. Well, what base are we allowed to use under our acidic conditions? Our nucleophile here, water, can also play the role of a base. So we're going to have another water molecule come along and accept that proton, reforming that hydronium catalyst. Okay, so we first looked at this reaction under basic conditions, where that first step was nucleophilic attack, producing that negatively charged oxygen. That's okay, because under basic conditions, we're allowed to have negatively charged intermediates. Under acidic conditions, though, our first step had to be to protonate that oxygen. That was a means of avoiding that negatively charged intermediate, because by protonating that oxygen, we allowed it to accept that pair of electrons and become neutral as opposed to negatively charged. All right? And we're going to see this a lot with our acidic condition mechanisms. They're always got a few extra steps in there because we have to do these proton transfer steps to help manage our charges. Right? In our basic conditions, we could just have nucleophilic attack and then protonate that negatively charged oxygen to form our Chem diol. We get the exact same product under acidic conditions. We just have that extra step to help us manage our charges. That proton transfer step to that oxygen. So we don't have negatively charged intermediates, we have positively charged intermediates. Okay, so we've taken the world of nucleophiles and looked at that before. Let's make a similar thing here. We're going to look at our nucleophiles. All right, and we're going to look at first our basic conditions nucleophiles. Okay, we want to divide these up based on that nucleophilic site. So we can have basic condition nucleophiles where our nucleophilic site is that oxygen atom. Everybody take a second, try to give me an example of a basic condition oxygen nucleophile. Right, like we just saw, hydroxide. Right, I mean, hopefully when I say base, the first thing that you think of is hydroxide. Those are basic conditions. Those make basic conditions, and they're also good nucleophiles, right? Strong bases and strong nucleophiles. Likewise, since this is organic chemistry, instead of having a hydrogen, I could have an alkyl group, those deprotonated alcohols or alkoxide ions. Those are also good basic condition nucleophiles. All right, in that same family of oxygen is sulfur. All right, what would be my analogous sulfur nucleophiles here? All right, if we take that hydroxide ion but just swap out hydrogen for its family member sulfur, that's also a good nucleophile. Same thing here, these deprotonated thiols. These are good nucleophiles under basic conditions. Right, and then there was a group that we were introduced to last chapter of hydrogen nucleophiles. And remember, that's kind of weird because hydrogen doesn't normally play the role of a nucleophile, but these special compounds, these hydrides, were an example of hydrogen nucleophiles. And if you go back and look at those mechanisms carefully, you'll note that they take place under basic conditions. We have these negatively charged intermediates. It turns out that our potassium aluminum hydride and our sodium borohydride are incompatible with acidic conditions. These are also basic condition nucleophiles. Oh, lithium aluminum hydride, I'm sorry. I don't know that it doesn't exist, but that's the common one. The other group 1 metal. All right, and then there were a few carbon nucleophiles that we were introduced to. There are a few special cases, one being that cyanide ion, certainly a good carbon nucleophile. All right, but that's just one molecule here, one particular ion. We can get a little bit more flexible with those deprotonated terminal alkynes. So if we use a really strong base, we can take off that terminal hydrogen of an alkyne. But then there was one extra flexible one that we were introduced to last class, last chapter rather, a carbon nucleophile. That's pretty special because it's got that metal ion in there as well, or that weird organometallic bond. And those are our Grignard reagents. Okay, we looked at these alongside our hydrides in our previous chapter, talking about reacting aldehydes and ketones to form alcohols. These are basic condition nucleophiles. You can convince yourself that we have these negatively charged intermediates when we do our reaction mechanisms. All right, importantly, we didn't really talk about it at the time, but Grignards are indeed basic condition nucleophiles. They are completely incompatible with acids. It turns out when you do these Grignard reactions, if you ever do them in the lab, you first take great pains to make sure that your glassware is completely bone dry, because any source of proton, even something like water, will react with your Grignards and effectively ruin it. It just kind of falls apart, all right? So these are only compatible under basic conditions here. There's one element that we're kind of conspicuously leaving off of this list here, and these are our nitrogen nucleophiles, all right? Something like these amide ions. Okay, these are certainly basic nucleophiles, but our nucleophile list here that we're trying to make is for our nucleophilic addition, specifically to aldehydes and ketones. All right, and it turns out that these nitrogen nucleophiles here, these basic nitrogen nucleophiles, are not compatible with our aldehydes and ketones. All right, and the reason for that is a little complicated, and we'll get to that in our next chapter. For right now, you're just going to trust me, and we're going to note that these are left off of our basic conditions list here. All right, certainly a base, certainly a nitrogen nucleophile, just incompatible with aldehydes and ketones. Cool. So then if we go ahead and make a similar list, but for nucleophiles that we would find under acidic conditions. All right, I want everybody to take a second. We did our basic oxygen and sulfur nucleophiles. Give me our acidic oxygen and sulfur nucleophiles. All right, so if I look here, this has this negative charge. If instead I added an additional hydrogen to make it nucleophile, to make it neutral rather, that would be my acidic condition nucleophile for that oxygen. Same thing here. If I take that alcohol, that alkoxide ion rather, and I protonate it to make an alcohol, that would be an acidic conditions nucleophile. Same thing with my sulfur nucleophiles. I can add an additional hydrogen, creating that neutral sulfur nucleophile. Add an additional hydrogen to create that neutral sulfur nucleophile, our thiols. Now, I can't play that same game with our hydrides. Our hydrides are kind of special compounds to begin with. But even if I take, for example, this cyanide ion, and I tried to play the same game and said, all right, let's just make it neutral. This is still not a carbon nucleophile here. What's wrong with this molecule that makes it not a nucleophile? What's the difference between this carbon atom and these other atoms that I have in my neutral nucleophiles? The lone pairs, right? There's no electrons to donate when we have a neutral carbon atom. So no, we don't have those same categories here. All right, instead what we have in addition under our acidic conditions are those strong hydrohalic acids, our HCl. I guess we should be good and give it its lone pairs, HBr, and HI. All right, these strong acids have these conjugate bases that are themselves weak bases, so they can exist under our acidic conditions and can play the role of the nucleophile. All right, so then given these nucleophiles here, let's try to predict our reactions. Let's just take a ketone All right, I'm going to mix it in with this nucleophile here. And everybody's going to take a second. I want the full reaction mechanism here. So step one, we're going to identify what our conditions are. Basic or acidic. Right, so when we're predicting our mechanisms, that's step one. Basic or acidic. This is indeed a basic conditions nucleophile. And then you're going to look and say, all right, well, what's my electrophile and what's my nucleophile in this first step? Who's attacking who? Where's my electrophilic site? Where's my nucleophilic site? All right, everybody take a second. See if you can't predict our products here for our reaction mechanism. Really predict the whole mechanism. All right, so what's my nucleophile going to be in this first step? My hydrogen sulfide ion, specifically that sulfur atom with its negative charge. And what's my electrophile? Well, rather, this is my electrophile, my ketone. What's my electrophilic site? That electrophilic carbonyl carbon. All right, so then our nucleophile is going to attack our electrophile. Okay, now importantly, that can't just be the only step that I do. Otherwise, I'm violating that carbonyl carbon's octet rule. It's got 5 bonds. So remember, what makes this carbonyl carbon so good at accepting electrons is that it can kick that pair of electrons up onto that oxygen, and it never has to break its octet rule. Okay? So we've seen these intermediates here before. Once that carbonyl carbon gets attacked, that oxygen has that negative charge because of that additional pair of electrons. All right, now we're going to give it a name here because we're going to see it over and over and over again. So, my carbonyl, when it started out here, was sp2 hybridized, meaning it was this trigonal planar geometry. Over here, now that it has 4 bonds, what's the hybridization on that carbon? sp3, which means it adopts a tetrahedral geometry. And so we call these intermediates these tetrahedral intermediates. All right, these will always form in our nucleophilic addition reactions. Whenever that carbonyl carbon gets attacked, we get this tetrahedral intermediate. Now we have this negatively charged oxygen. This pair of electrons would love to be able to come back down, but it can't violate that carbon's octet rule. And none of these here are really good leaving groups that could get kicked off. So instead it's kind of stuck until we have some source of proton that we give it to create an alcohol. Ideally, we can use the neutral version of our nucleophile. And so in this case here, we can just toss in some of that hydrogen sulfide. And that can be our source of nucleophile to create our product. All right, this discussion of acidic and basic nucleophiles, as well as our product here that we have with this alcohol group. This should remind us a lot of our epoxide reactions, all right? A signature of those epoxide reactions was that hydroxyl group and that nucleophile were located 2 carbons away from one another. So what's a big difference here with our aldehydes and ketones? That hydroxyl group and that nucleophile are now bonded to the exact same carbon, what was formerly our carbonyl carbon. All right, but very similar overlap between those 2 reactions. Let's do another one here. We're going to keep this same ketone. All right, this time we're going to react it with another basic nucleophile, our Grignard reagents. All right, this should be a review of what we did last chapter, so everybody take a second and give me the mechanism here. All right, so Grignards, if we're going to find our nucleophile and our electrophile. Grignards are nucleophiles that are kind of hard to spy. They don't have that net negative charge that we're used to looking for. They don't even have lone pairs. We just have to know, we have to be good at recognizing that this carbon here has a ton of electron density because it's in that bond with that very low electronegativity metal. So Grignards, we just got to be able to recognize as strong basic nucleophiles. The other thing about Grignards is since they don't have that pair of electrons, that lone pair, we have to start our bond, or rather our electron pushing arrow at that magnesium carbon bond. But just like before, we're going to kick up that pair of electrons onto that oxygen. And we're going to form these. We didn't even name it at the time, but we saw the same tetrahedral intermediate that we're going to form. All right, importantly, my electrophilic carbonyl carbon is going to form a new bond with that nucleophilic Grignard carbon. And just like before, I need some source of proton to be able to protonate my oxygen. Unlike in our previous example, I don't have a protonated version of a Grignard to use, which is why when we do our Grignard reactions, you'll notice that they always have 2 steps associated with them. The other step, so this would be step 1, the second step is to add in that source of proton, right, that hydronium ion, specifically to protonate that alkoxide oxygen. So that's why we have 2 steps in our Grignard, because we can't just add in, there's no protonated Grignard that we can use. All right, again, hopefully review from our previous chapter. All right, but what we've done is create this alcohol, and again, we've added our nucleophile to that same carbon where we find that alcohol group. So these are our basic nucleophiles. Again, with our basic nucleophiles, that first step is nucleophilic attack. because we form that negatively charged oxygen, which is allowed under basic conditions. We need to protonate that oxygen to make our alcohol product. Ideally, we can use just a simple protonated version of that nucleophile. There are some, our Grignards, as well as we can note our hydrides, where that is not possible. And so instead, we have to do a second step where we follow it up with that source of proton in order to create our alcohol group. All right, so now let's do another one. We're going to actually take this same alcohol. I'm sorry, not alcohol, same ketone. And we're going to treat it with that H2S. And what we're going to see is we get the exact same product here. All right, but this nucleophile isn't a basic condition nucleophile. This is now an acidic conditions nucleophile. All right, as we talked about before, my first step cannot be nucleophilic attack, or I'd create that negatively charged tetrahedral. So instead, we're going to have to use our acidic conditions here. All right, if it's not stated otherwise, we can just use sort of default to hydronium as our acid. All right, but everybody's going to take a second and give me my mechanism here under acidic conditions to create that same product, that thiol alcohol product, or mercapto alcohol product, I guess. All right, so as we said, we can use proton transfers to manage our charges. Importantly here, if I look at these three in my mixture, hopefully this one jumps out as the best electrophile here. So it can donate that proton, kick off that water as a leaving group. Right, so now we have this protonated ketone here, meaning that oxygen has a positive charge. So now my nucleophile can come and attack that electrophilic carbonyl carbon. And when that pair of electrons jumps up onto that oxygen, it doesn't do so as a negative charge, it does so as a neutral hydroxyl group. one of the big differences here is that since my nucleophile was neutral when it attacked, now I've turned that lone pair into a bond, giving it that positive charge. So in order to get to my final step here, I'm going to need to deprotonate that. This will be reversible. All right, and so our base, we got a good base here, or a weak base, water, can deprotonate that thiol, jumping that pair of electrons onto our sulfur. And again, we see that we have more steps in our acidic condition mechanism because we use these proton transfer steps here to manage our charges. All right, same product though. Okay, again, a lot of overlap between what we saw with epoxides, but even easier than epoxides in that we don't have any regioselectivity to deal with here. The only thing that can be attacked, our only electrophilic site, is that carbonyl carbon. All right, one other thing to note about our acidic conditions nucleophiles versus our basic condition nucleophiles are these are all negatively charged, whereas these are all neutral, meaning that our basic nucleophiles are stronger than our acidic condition nucleophiles, right? So then why do we get away with using these weak nucleophiles under acidic conditions? Because importantly, when we protonate this oxygen here, it makes that carbonyl carbon an even better nucleophile, electrophile. Right, that protonated oxygen able to accept electrons, even better. So then our carbonyl carbon is a better nucleophile, better electrophile. Holy cow. So it can react with those neutral nucleophiles like our hydrogen sulfide. All right, cool. So one that we're going to kind of look at special here of our acidic nucleophiles are these alcohols, because these produce the products that you expect, but then they also go kind of one step further. So let's take a look. This is what we call our acetyl formation. All right, this is what we get when we react aldehydes or ketones with alcohols, specifically under acidic conditions. Right? So everything sort of starts out exactly as you would expect based in analogy of what we did in our previous reactions. All right, so I'm going to have these acidic conditions. I'm going to have this alcohol nucleophile. All right, I want everybody to take a second and give me the reaction mechanism to produce what we would expect here, given what we did in our previous example. So we can't do nucleophilic attack first. We first have to protonate that ketone oxygen. Now we've turned it into an even better nucleophile. And more importantly, when that tetrahedral intermediate forms, we don't have any negative charges. Oh, whoops, nope, we still have that proton there. So we got a positive charge there. So we got one more step here, which is to simply deprotonate that, what was formerly our alcohol nucleophile. We need some weak base to do it. We can default to water here. And so based on what we've seen previously, this is what we would expect to form, where we have that alcohol group, or what was formerly our alcohol, bonded to that formerly carbonyl carbon, and that carbonyl oxygen forming that hydroxyl group, right? So this would be our product that we would expect based on everything that we've done up until this point. This is what's called a hemiacetal. And it turns out that our reaction does not stop here. So this is indeed formed, all right, but it doesn't stop at this hemiacetal here. We're going to keep on reacting here to form what we call an acetal, and let's take a look at that real quick. And so looking at this acetal here, what do we think we're going to have to do in our reaction? What does it look like we've added on to this molecule here? Going back to our original reaction mixture. Here's when I've added that first alcohol nucleophile. Now if I look at my acetal, what do we think we're going to have to do? What's the difference between an acetal and a hemiacetal?
Use the water to take that hydrogen away.
So we're going to have to add this group on here, right? Can we play the spot the difference? We can all convince ourselves that this is the difference between the two. Where did those carbons come from? Another alcohol molecule, right? So now we're going to react to yet another alcohol with our hemiacetal, giving us that extra 2 carbon group on there. So yes, another molecule of alcohol here. Remember, pencil and paper, it looks like we only got 3 things present here. Of course, in solution, there's plenty of each of these floating around. So yes, there's a ton of excess alcohol here. Okay. So great, let's say I can recognize that I'm supposed to add another alcohol. So let's just go ahead and do our nucleophilic attack. This gets me pretty freaking close to this acetal here. I just have this extra proton on there. All right, but this is not what happens. Why not? This is a perfectly fine intermediate here, right? But what did I do that was illegal at this step? What else did I create?
OH is not a good leaving group.
Yeah, so not a good leaving group. Not only that, but remember, what conditions are we under? Acidic conditions. If I follow my electron pushing arrows here, in this step, I would have had to have kicked off a hydroxide ion, which, yes, is both a terrible leaving group and just flat out not allowed under our acidic conditions. So again, we can't have nucleophilic attack first. So what did we say that we did to manage our charges? What's this strategy that we've had for managing charges?
Use the water to make another H3O.
We got plenty of H3O floating around. We don't even have to make another one, right? There's plenty of those floating around. But remember, if we ever get in this situation where like, crap, I know I need to make this new bond, but if I do that right away, I'm going to have a negative charge. How do we manage our charges? We're just going to have to do more proton transfer steps, right? So I can't kick off that hydroxyl group or it'll be that negative charge. So what am I going to do to it beforehand? I'm going to protonate it. So yes, there are plenty hydronium ions floating around in solution. So I'm going to take another one of those hydronium ions and I'm going to use that to protonate that group I'm trying to get rid of. So this will be my intermediate here with 2 hydrogens and a positive charge. All right, and we played this same game with our alcohols. Hopefully we all recognize this here to be a good what? A good leaving group. All right, so let's think of 2 possible paths here forward. Okay, we know we need to kick off that leaving group, right? All right, so let's first look at our intermediate if we just kick off that leaving group. That's all we do in this step. Everybody take a second and draw me my intermediate here if we kick off that leaving group. Boom, all right. That leaving group leaves, takes that pair of electrons with it. That leaves us with a carbocation intermediate. Okay, it turns out that there's a better way to do this flow. All right, we are going to kick off that leaving group. Okay, but at the same time, we're going to take this pair of electrons from this oxygen and bring it down here. All right, I want everybody to take a second and follow my electron pushing arrows. What have I done in this step here following those electron pushing arrows? In both cases, I kicked off a water. All right, but what's the difference with what I'm left with?
Double bond.
Yeah, that's a bond formation arrow there. So yep, that bond formation arrow creates a carbon-oxygen double bond. My oxygen is going to need what? That positive charge. All right, so these both have accomplished this same goal of kicking off that water leaving group. So check, check. Okay? One of these intermediates, though, is more stable than the other one. So one of these paths are more preferable than the other one. And which one is it going to be here? All right, so let's kind of ration through it real quick. In both of these cases, I have a positive formal charge. And there's no way to avoid that, right? We're going to have a formal charge on our intermediate. But we're allowed to have positive formal charges because this is acidic conditions. Positive intermediates are allowed. So is it going to be more stable on this oxygen or on this carbon here?
Oxygen.
Yeah, why the oxygen?
Carbocation is very unstable.
Very unstable, and why? Right? What's the difference between when oxygen has a formal charge and when carbon has a formal charge? Count the total number of electrons in those octets. All right, what's the difference between a carbocation with a positive formal charge and an oxygen with a formal charge? Carbocations have incomplete octets. Right? We do see carbocation intermediates, but yes, they are very unstable because they have incomplete octets. If instead I put that positive charge on my oxygen, well, oxygen has a complete octet with that formal charge of +1. So both of these accomplish the same goal. Like if you gave me this on an exam, I'd be like, good job. That was a really good guess there, right? That's a very logical step forward there. It just turns out that there's a better way to do it. And that is to have that pair of electrons on that oxygen come down at the exact same time. And if we look here, this looks a heck of a lot like a carbonyl group with a pair of electrons that can jump up. And so that's exactly what's going to happen in this next step here. Just to kind of zoom out, move this over. Now we get to have our nucleophilic attack with that second alcohol. Kind of space it out. Okay, and because that oxygen's positively charged when that pair of electrons jumps up, we don't have a negatively charged intermediate, we have a neutral intermediate. Try to squeeze this in as best as possible. All right, we're not quite there. We have one more proton transfer step, but I believe in y'all, you can do that. All right, so we got one more intermediate here that has this extra hydrogen that we would remove in order to form our acetyl here. This reaction gets a special shout out in organic chemistry because it turns out to be an incredibly important reaction in biochemistry. When your body links sugars together to store them as starches, it is using this reaction right here, this formation of these acetyl bonds. Cool.